Another example of a volume of revolution. So we're going to revolve the area bound by f of x equals e to the x squared in quadrant 1, 0 to long 3 about the y-axis. Okay, usually if we see y-axis, we know that if it's a vertical axis, we should probably use the shell method, remembering that the shell is going to be volume is 2 pi integral a to b, x, which is the radius, f of x, which is the height, dx is the distance between each of those, theoretically 0. Graph in quadrant 1, e to the x squared looks something like this. Okay, probably a little bit steeper. And we know we're going from 0 to natural log of 3. All right, and if we graph this and just think about what the volume of revolution would look like, here's one of the shells, and then we have another shell, probably a little bit longer than that. All right, but you guys get the idea that we're just using a whole bunch of shells. All right, so another shell, and then another shell, and another shell, etc., to be able to find the volume for this. All right, the good news is we have the function, the bounds, and we know that it's going to be the shell method. And so the setup for this, 2 pi integral 0 to ln 3 of x, which is the radius, e to the x squared, which is the height, and the theoretical distance between those dx. Fortunately for us, this is a u substitution problem. If we let u be equal to x squared, this implies that du is going to be our 2x dx. And that's perfect because we have dx, we have x, and we have a 2 on the outside. So du can kind of substitute for all three of those nicely. And the only things we'd have left is just pi and then e to the u. So we have our pi out front. We have a to b because we're changing into u. And we have e to the u du. Antiderivative of e to the u is e to the u. And be careful with this one. All right, so we're going to back substitute. We're going to get pi e to the x squared from 0 to ln of 3. Now, we have to be careful with this because we know that e's and ln's are inverses. We also have to remember that 0 is not going to cancel out because it's not a polynomial. Okay, so we don't want to make the assumption that 0 is always going to cancel out. So, fundamental theorem of calculus, e to the ln of 3 squared minus pi e to the 0 squared. Right? Now, fortunately, this just becomes 1 because it's e to the 0. So this is just going to be pi. This we can't do anything with. All right. We know that e's and ln's cancel out, but this is e and ln squared. All right. So we're just actually going to have to leave that as pi e to the ln of 3 quantity squared. The only other thing we could possibly do is factor out a pi, which really doesn't help us. It's still as ugly as it was before. So ln of 3 minus 1, and the ln of 3 is going to be squared. All right, so not too difficult, okay, to be able to evaluate our volume. All right, but we want to make sure that we understand, first of all, about the algebra rule here, that because this is quantity square, we can't do anything about it. All right. Also, the u substitution technique. Okay, we can't forget about our techniques of integration. Another example is to be able to find the area revolved at the y-axis. All right, and again, since it's y-axis, we're going to have to be able to do the shell method. Okay, and we have a bit of a weird function. It's not too bad. F of x equals 2 quantity 1 plus 2x squared to the negative 1. And so when we set up our integral, we have our bounds, we have our function, and so this is going to be 2 pi integral from 0 to 2, function 2, 1 plus 2x squared, the minus 1, we have x, and then we have dx. We could factor that 2 out, right? And we could notice that we would end up with 4 pi 0 to 2, and putting this in the denominator, since it has a negative 1 power, x over 1 plus 2x squared dx. Similar to the previous example, this is going to end up being a u substitution, and it actually works out really nicely. If we let u equal the denominator, 1 plus 2x squared, the derivative is 4x dx, And notice that we have x, dx, and 4. So all those are going to be substituted are going to basically be substituted in for du. And then this is just going to be our u. We have pi integral a to b, because we have a change in variable. We have du for the 4, the x, and the dx. And then we have u for the 1 plus 2x squared. This is going to be a natural log. All right, so we're going to get pi ln. Technically, it's the natural log of the absolute value of u. All right, from a to b. Remember that our bounds were from 0 to 2. Our u is 1 plus 2x squared. So we get pi natural log 1 plus 2x squared, right, from 0 to 2. And then if we substitute 2 and 0 back in, all right, again, 0 does not wipe it out yet. Okay, so we're going to get pi ln 1 plus 2 times 2 squared minus pi ln absolute 1 plus 2 times 0 squared. All right, so some good news about this. 2 times 0 squared is 0. And so we have pi ln of 1. And ln of 1 is 0. So this whole thing is just going to wipe out. Right? In the parentheses here, we get 2 times 4, which is 8. 8 plus 1 is 9. So we end up with pi ln of 9. All right, and that's going to be our volume of revolution for this one. Okay, so not too difficult, but just 2 examples of being able to use a u substitution, which is a common technique when when we have these transcendental sort of functions or these algebraic functions that aren't polynomial types with respect to the shell method. Okay, in the next example, we're going to take a look at a singular being able to bind by 2 functions and see how that works.